In this video, we're going to talk about how the pH scale was arrived at, how pKa and pH scale are all based on what we call the self-ionization of water. Now, that term is sometimes also referred to as autoionization or autoprotalysis, right, relating to creating of protons. So water has this really fantastic ability to behave as both an acid and a base at any given situation. So when two water molecules get together, you create both acid and base scenarios. Okay, so it's kind of a funny thing. Water can act as both an acid and a base in given situations. And in a solution of water, pure water, this is happening all the time. So the H3O plus is becoming H2O, and the H2O is becoming OH minus, and the OH minus is going back to H2O. It's a very dynamic equilibrium. And because it's in equilibrium, it has a K value, and we call this KW. Okay, K for water, W for water. And that equilibrium has a value of 1.0 times 10 to the minus 14. Okay, now it's important to understand that this is in pure water and at a given temperature. Okay, KW will fluctuate depending on the temperature of the water. Okay, for most problems that we're going to deal with, you can assume 25 degrees Celsius. But you can be thrown questions where the question might say, at 20 degrees Celsius, KW has such and such value, which will be slightly different. And then you can just apply the principles that I'm about to go over to that scenario. Okay, but most of the time we're going to assume pure water at 25 degrees Celsius, KW is equal to 1 times 10 to the minus 14. So how do we deal with this? So KW, if we write an equilibrium expression for it, comes out in a very handy fashion for us to use in our acid-base problems. Okay, because our H2O liquid, liquids don't go in a K expression. So the K expression here is just related to the H3O plus and the OH minus. Okay, so if I needed to find one or the other, I can use this relationship. So that means that H3O plus times OH minus equals KW. So if that's the case, in pure neutral water, and that's very important, pure neutral H2O, we have a value of 1.0 times 10 to the minus 7 for each. Okay. If we're in neutral situation, my H3O plus should be equal to my OH minus. If they're out of balance, we're not neutral. Okay, that neutral part is very, very important to this relationship. Okay, and we can say that, so if this is my H3O plus, then the pH is the negative log of 1 times 10 to the minus 7, which equals 7. So this is the center of the pH scale. Right? So that is the only definite point on the pH scale. Okay, 0 and 14, which are the opposite ends of the scale, are only sort of, they're not actually limits. Okay, you can have pHs of less than 0 and greater than 14. Okay, so for example, what's the H3O plus concentration for pH equal to -1? We'll find that so if -1 equals the negative log of x, then x equals 10. Right? So that means that H3O plus is 10 molar, which is easy to make in the laboratory. For example, concentrated HCl is 12.1 molar. Okay, so concentrated HCl will actually have a pH of less than 0. Okay, so let's use this relationship and do a couple of practice problems. So if the OH minus concentration of a solution is 4.92 times 10 to the minus 3 molar, what is the H3O plus concentration? Okay, the easiest way to deal with this is to take our relationship of H3O plus and OH minus equals Kw. So H3O plus is simply Kw divided by OH. Right? So I can just plug in the concentration of OH and solve. Over 4.92 times 10 to the minus 3, which gives us a concentration of 2.03 times 10 to the minus 12. Okay. Alternatively, I could solve this another way. I could find POH first. So there are lots of ways that we can solve these problems. So the POH will be 2.308, right? And the pH is 14 minus the POH. So the pH is 11.692. Okay, so if I wanted to find the H plus or the H3O plus from the pH, I can do that quite easily. Is 10 to the negative pH, right? Do the antilog. 10 to the negative 11.692 gives us a value of 2.03 times 10 to the minus 12 also. Okay, so there are multiple ways that we can go about solving these problems using the relationships that we have. The relationship of pH and POH, the relationship of H3O plus and OH minus. Okay, so since we have this relationship to Kw, since OH minus times H3O plus equals 1 times 10 to the minus 14, I can say the negative log of the OH minus plus the negative log of H3O plus equals the negative log of Kw, right? Because when I take logs of everything, if I multiply the two things, then it's the same thing as adding the logs. So this is the same thing as POH plus pH equals 14. That's actually how we get it. Okay, so let's do a problem, a realistic problem, one that actually sort of has some environmental implications. So here's our example problem. So let's say that some person that is against the environment comes along with a big old bottle of concentrated HCl. So let's say that person dumps 2 liters of concentrated HCl, which is 12.1 molar. In a pond, in a 20,000 liter pond. Will the pH go below 4.5? Boy. All right, 4.5 is where fish die. Okay, that's the lower limit to a livable environment for aquatic life. Okay, so let's take a look at our ionization equation. HCl aqueous plus some liquid water. And HCl is a strong acid, so the only thing that it does is come apart. So I use a single-headed arrow, right? That's why we want to know the list of strong acids so I can understand how to treat this problem. Okay? So 100% ionization, right? Ka is large, pKa is small. So all I really need to know to find the pH is what is the concentration of H3O+. Right? So I have 2 liters of acid, moles of HCl per liter is the concentration of our acid. So then I have 24.1 moles of HCl, right? Our H3O plus concentration comes from the relationship of how many protons there are per molecule. 24.1 moles of HCl, and we have 1 mole of H plus per mole of HCl. So I have 24.1 moles of H plus. Right? Remember I said that H plus and H3O plus were kind of interchangeable. Okay? So that tells me how many moles. That's not the concentration of H3O plus. That's important. Okay? In order to calculate pH, we need concentration, not just moles. Okay? So I've got 24.1 moles of H plus in a 20,000 liter pond. So I get a concentration of 1.2 times 10 to the minus 3 molar. Right? So our pH is the negative log of 1.2 times 10 to the minus 3 gives us a pH of 2.92. Pond is doomed. Okay, our environmental terrorist has succeeded. Right? So dealing with strong acids, strong bases is very straightforward process because you can find the ion concentration directly from the concentration of the solution. Okay, so we're going to stop there for this video, and we'll come back on our next video talking about how to deal with conjugate acids and conjugate bases and evaluating their strengths.